Welcome back, everyone. I'm Michelle Sanner. Today, we are talking about chemical bonding. We're going to go over the 3 different types of bonds we're going to be talking about this year. And if you see this little pink cloud icon, that's just a remember icon. Maybe it's something that should be reviewed to you at this point. So let's get started. We're going to talk about the 3 different types of bonds you can experience this year in chemistry. But first, I think it's important that we articulate what a chemical bond is. So here's our textbook definition. A chemical bond is a mutual electrical attraction, so the attraction between protons and electrons, between the nuclei and valence electrons of different atoms that bind those atoms together. So you could have 2 atoms bonded together creates a chemical bond, but you can also have multiple atoms bonded together, different types and numerous counts of each one. Remember, a valence electron is the outermost electrons that tend to participate in bonding. And they do that, as we talked about yesterday, they do that because they're trying to achieve some sort of stability. And typically the way that they're most stable is when they're able to form a full octet of 8 electrons shared between 1 or more elements. Remember that nuclei is the plural of nucleus as we work through this exercise. So why would atoms bond? Well, bonding creates more stability. And we've discussed at length this idea that the universe tends to want to fall to a stable state. So atoms tend to bond to one another if it's energetically more favorable, if it's more stable to do so. And if it takes more energy to create the bond, they're unlikely to do that. Bonding minimizes potential energy. So that's the energy associated with position. So bonding is able to bring us into an energy well. We looked at that in our potential energy diagram the other day. Bonding minimizes this potential energy to create more stability. The first type of bond we're going to discuss is an ionic bond. So the chemical bonding that results from the electrical attraction between cations and anions is called ionic bonding. So cations and anions are another term for the type of ions we might experience. So cations, those are positively charged ions. Those are ones where there's more protons than there are electrons. And anions are ions in which there are more electrons than there are protons. So ionic bonds are interesting because they actually involve a full transfer of electrons as opposed to an equal sharing of electrons. So an example of an ionic bond can be seen right here down below. Here is a nucleus that is more electronegative. It's able to attract electrons to itself better than its neighbor over here, this little smaller nucleus. But remember, we are looking at electron density clouds here. So in this ionic bond, the electrons for this positively charged ion have jumped over to join the electron distribution probability cloud, this orbital here, of this other nucleus. So something about this element is better able to attract electrons to itself than this element. This could have to do with the atomic radius. It could have to do with electronegativity or ionization energy or any of the other periodic trends that we've discussed. So ionic bonding, transfer of electrons between two or more nuclei. Here's an example, a visual of an ionic bond. You've got this purple atom A, this purple atom B, and an ionic bonding, electrons are transferred from A to B, and this causes B to become more negative. And you can see it's gotten larger, not because things have been added to its nucleus, but rather because its electron orbitals, the area electrons are likely to occupy, has expanded with the addition of a new electron. So in this type of bond, you will have cations and anions stuck together in some way. They're joined together by their virtue of having shared and transferred electrons from one to another. So atom A, let's take a look at what happened here. This purple atom A went from neutral to a positive ion. So it lost electrons in the process. It has given away one of its electrons. Atom B, on the other hand, started out as a neutral molecule and then gained negative electrons to become a negative ion. It gained an electron by virtue of forming this ionic bond. Ionic bonds happen when you have a metal and a non-metal. So one of your skills is being able to look at your periodic table and see 2 different elements and identify based on their metallic or non-metallic properties whether or not they're going to form an ionic bond or a different type of bond that we're going to discuss today. So types of chemical bonding. Our second type of bond we're going to discuss is covalent bonding. Co meaning you know, like cooperation or coordinate. So it has something to do with the joining. This covalent bonding results from the sharing of electron pairs between two atoms. Covalent bonding is sharing of electrons versus the ionic bonding that was a full electron transfer. You know, Halloween's coming up, and I like to use this analogy, and maybe it'll work for you. I'm the oldest sibling, so since I was the oldest, you know, I was kind of in charge of my younger siblings. And after Halloween, you know, I may or may not have been able to conduct better trades than my younger siblings were. So it was always my MO to try to get myself some extra Reese's peanut butter cups. So in covalent, you can think of electrons like our Halloween candy. And this covalent bonding, this sharing of electron pairs between two atoms, isn't always an equal sharing. Just like when me and my brother and sister would dump our Halloween candy out at the end of the day, being the older sibling, I tended to walk away with a little bit better candies than they did, by virtue of the fact that I had some influence. So talking about this is just a metaphor that I'm going to use to discuss the different types of covalent bonds and ionic bonds. So covalent bonding, it's important to understand, electrons are shared between two or more nuclei. Here's an example. Atom C, this little green atom, and atom D, two different atoms, when they are able to share pairs of electrons, they come together, but notice there's no net charge. So unlike the ionic example, we don't have positive or negatively charged particles at the end of this. We just have one compound that is overall neutral. So electrons are shared by both atoms. So imagine in covalent bonding, Halloween trick-or-treating's over, my brother and sister and I all dump our candy out into the middle of the living room floor, and we divide it up equally. Well, that would be an equal sharing of candy. And likewise, some atoms equally share their electrons, but not always. It's important to note that covalent bonds are always shared between a nonmetal and a nonmetal. So I could give you two different elements on the periodic table, and you should be able to, but only by virtue of knowing whether they were metals or nonmetals, decide if they would participate in ionic bonding or covalent bonding. So rarely is something purely ionic or purely covalent. And only when we compare an atom's electronegativities, that is to say that using the Pauling scale, we can determine what type of bonding is most likely occurring between two different elements. Remember, and this is a review, that electronegativity is a measure of an atom's ability to attract electrons to itself. I often use the metaphor of a popularity contest. You have two nuclei, one of them is going to be a little bit more popular with the electrons by virtue of its size, by virtue of its number of protons or some other characteristic, and another element might be less likely to attract electrons to itself. So there's some sort of unequal sharing. Draw this chart in your notebook, because this is going to help you very much to easily organize and visualize the different types of bondings and quickly reference what's going on in terms of their characteristics and the types of atoms involved. I'll give you a second to write that down. So pause the video and write that down on your piece of paper. So you may wonder, what was that electronegativity difference and how do I calculate it? Well, to calculate the electronegativity difference, it's simply, we just simply use the Pauling scale of electronegativities, and you subtract the element that has the smaller value from the element that has the larger value. So let me show you an example. Is the bond between fluorine and cesium ionic or covalent? So again, we're going to use these difference in electronegativities. After I do the subtraction, it's above 1.5, I can reasonably assume that I'm talking about an ionic bond. If it's between 0.3 and 1.4, we're talking about a polar covalent bond. And if it's between 0.0 and 0.2, we're talking about a nonpolar covalent bond. So let's take a look. Fluorine and cesium. Where do I find this information? I'm just going to jump ahead to our Pauling scale and look for fluorine. Fluorine's electronegativity value is 4. Cesium's electronegativity value here is 0.7. And again, this diagram comes from your text. So jumping back, I take the larger number 4, subtract it, the smaller number, and I get a value, 3.3. And if we look back at our table, we'll see that this falls within the range of an ionic bond. So that's the easiest thing you can do. Just calculate electronegativity difference, do a little subtraction, and you'll be able to just decide based on this chart what type of bond we're talking about. So let's talk about those two different types of covalent bonding. We referenced them a moment ago on our table, but what do they mean? So when two atoms have significant differences in their electronegativities, the electrons are more attracted to the one that's more popular. They're attracted to the more electronegative atom. And we've touched on this a little bit, but let's think about what's really happening here. These bonds are said to be polar, and what that means is they have an uneven distribution of charge. This small symbol, this lowercase delta, is shorthand for partial. It means like somewhat. So the more electronegative atom is given a negative delta because it attracts electrons better. So it's partially negative. So we give it this small sign. The less electronegative element, according to our Pauling scale of electronegativity, gets the distinction of having the positive partial sign in front of it. So that means it's partially negative and partially positive, respectively. So these polar covalent bonds, these bonds that involve an unequal sharing of electrons, can be visually represented like this. So there's our small symbol, partially positive, partially negative. Again, these do not represent the nuclei of the element. Instead, they represent the electron cloud, the probability that an electron is likely to be in this location. And you can see for this more electronegative element here, it tends to be partially negative. It's not fully negative, it's not an anion. It's just that at any given point, it's more likely to have electrons nearby that nucleus compared to this other partially positive nucleus. So this one is better able to attract electrons. This one is less able to attract electrons. If I think about my analogy, my Halloween candy analogy, I can tell you that, you know, in my family, at least as the older sibling, our Halloween candy sharing was a little bit more like a polar covalent bond. I'm a lot older than my siblings, so I could barter a whole lot better and end up walking away with more Halloween candy at the end of the evening after we divvied it up amongst ourselves. Very rarely are you going to have fully equal sharing, non-polar covalent bond. And very rarely in siblings are you going to have perfect sharing if you were to split all your candy. Let's take a look at what a non-polar covalent bond would look like. Non-polar covalent bonds, and this might be a little bit counterintuitive because you have polar means not equal and non-polar means equal. So that's kind of funny. Non-polar covalent bonds are those covalent bonds in which the bonding electrons are shared equally by the bonded atoms. And this results in a balanced distribution of electrical charge. So looking at our diagram, we can see this black dots represent two nuclei. These two nuclei are equally electronegative. They're equally able to attract electrons to themselves. So you end up with a perfectly balanced overall molecule like this. It doesn't have any charge on one end, doesn't have any charge on the other end, unlike this polar bond, which is more negatively charged on this end, more positively charged on this end, or even our ionic bond, which is fully negative. It's a full anion on this right-hand side and a full cation on this left-hand side. So I can't think of very many sibling relationships where things are split completely equally. But if I had dumped all my Halloween candy into the pot with my brother and sister and we divided it up exactly equally, well, that would be a better metaphor for non-polar covalent bonding. So in summary, non-polar covalent bonds are characterized by an equal sharing of electrons. They always involve metals and nonmetals, and you're looking for electronegativity differences between 0.00 and 0.2. Polar covalent bonds, on the other hand, share their electrons, but unequally so. One nuclei is better able to attract electrons to itself than another nuclei. These, again, are characterized by non-metal and non-metal elements bonded together, and you're looking for a difference in electronegativities between 0.3 and 1.4 using your Pauling scale. Finally, in ionic bonding, electrons are completely transferred between one element and another. This results in the formation of ions, cations, and anions. These are characterized by a metal bonding with a non-metal, and you're looking for electronegativity differences of 1.5 and up. So the next time we meet, we'll practice more with calculating the electronegativity difference and identifying whether an element is polar covalent, non-polar covalent, or ionic. I hope you're doing well and have a great day.